everyone. Thank you very much for the invitation to this workshop. I will talk very briefly about some gaps between federated learning optimization theory and practice. And before we start, a small advertisement from my side. At the end of this month, I will move from EPFL to CISPA. And if you're interested to collaborate or to work with me, please reach out. In federated learning, we aim to train a central machine learning model, for instance, on a server, by accessing data that is stored on different client devices. And we do not want to send all this data to the server, but we want to train the machine learning models in such a way that the private data never leaves the client device. So we can formulate this training task as a minimization problem. For instance, in this form, where I say that the objective function, so the loss function, can be split into n components corresponding to the clients. And so each client just holds one share of this objective function. Very often we use the same loss function on all the clients, but of course, the data is very different on each client. And we now look at algorithms that are efficient in terms of number of computations, but also in terms of communication that are needed between the server and the clients. So the base algorithm that we often consider, or variations of this base algorithm, is a stochastic gradient descent. In stochastic gradient descent, we just need the assumption that we can query a uniform sample of our data set, of our training data. And then with this sample, this can be, for instance, just a single data point or a mini batch of data points. We can then compute the gradient of the loss function and update our model parameters slightly by following the negative direction of the gradient. Under some assumptions, we can prove that this stochastic gradient descent algorithm converges. For instance, very standard is to assume that the variance is bounded and that the gradients do not change too quickly when updating the model parameters. So this is the smoothness assumption. Under these assumptions, we can prove that SGD converges to a stationary point after this many gradient computations. And of course, under stronger assumptions, we can prove better rates or just get better guarantees. So if you see a result of this form, you should keep in mind that very often we give these results for very specific outputs of the algorithm. Here, the output might be different from the last iterate that you might use in practice. And also important is that these results depend on the optimal choice of the step size. So it basically includes already step size tuning. And I think more importantly, we are not sure if these assumptions hold in practice. So this is just if these assumptions hold, then we get these guarantees. So let's go back to the federated learning setting. In federated learning, we need to communicate between the server and the clients. And these connections, this communication has to happen, for instance, over the internet or over mobile connections. So we want to keep the number of communications around very low. So if you would just implement this mini batch SGD, where we get maybe one data sample from every client, and then the clients have to send these gradients back to the server, this is a very communication heavy algorithm, because for every update, we need one communication round. So one way to address this is, for instance, to just increase the batch size on every client, and then just send back gradients computed over larger batches. And another alternative is to look at local update methods. So in a nutshell, these local update methods, they update the parameters of the local models already directly with the gradients that they compute on their local data. So why should this be better intuitively than computing large batches? Well, if we do these sufficiently many local steps, each client converges to a good local solution. So at least they make some progress compared to just increasing the batch size. But on the other hand, there's a overfitting of the local data is also a problem in practice. So for instance, when we look at the convergence guarantees, we often see that, or we can prove that the local SGD is under the standard assumptions worse than mini-batch SGD. I mean, the right comparison is a bit tricky and one needs to pay attention to details. So please have a look at this work by Blake Woodworth and co-workers. So as I mentioned, these local updates, they are caused by data dissimilarity. So if two clients have different data, then of course they also have different preferences and they slightly converge to different model parameters. And there are now many algorithms have been designed to also address this data dissimilarity issue. So just to give a brief overview, so there are a class of algorithms that can mitigate this effect of this bias or this drift. And they basically can now match the convergence guarantees of mini-batch SGD, or in some cases also be better. So what I've not mentioned in this talk, of course, the other aspect is client sampling. We don't want to talk to all the clients every round, so we just sample a subset of these clients. There's been a bit of a theoretical avenue to really prove that these local update steps make any sense. And currently, the understanding is that if we make additional assumptions on the objective function, for instance, that the functions are quadratic or the Hessians of these functions are similar, then we can prove that local steps are indeed better compared to computing just a large mini-batch. And of course, if we can also think about different algorithms, not just SGD, but maybe what can we do by querying higher order derivatives or what else? And I think that there have been a lot of advancements made on the optimization side. So we have a very good understanding of algorithms, their convergence guarantees, often with lower bounds. So we know we have the best kind of algorithms for the given set of assumptions. But I think we should maybe step back a bit and start thinking, do these assumptions really hold in deep learning? Or do they really cover the deep learning setting well? And I think there are some gaps that we could address, or yeah, for some gaps we are maybe a bit closer, others are a bit more difficult. So I think we should do some effort to maybe rethink these assumptions, because these data dissimilarity assumptions, they have been developed a bit ad hoc, just by looking at the proof, and then we get some criterions from these proofs. What could be good assumptions to measure data similarity? However, this is not very, I don't know, it's not maybe not very inspired by practical measures. So I think that there is a bit of a gap there. And of course, one could also look at more proofs that more closely reflect what's happening in practice. So for instance, we often assume we can select these clients uniformly at random. But in practice, this might not be possible because some clients are rarely available, maybe just 1 hour a day. And some clients do not respond to our requests. So how can we guarantee that we are still learning the right thing under these more practical, more difficult assumptions? There's also these convergence guarantees that we establish. They're just proving that the algorithm converges to a stationary point. So we cannot really compare the algorithms only by looking at the theoretical results, because these stationary points might be, to some extent, useless for our machine learning objective. So we do not know if we generalize well at this particular stationary point or not. So we should work towards a bit better understanding of optimization guarantees, but also then machine learning guarantees like generalization performance on unseen data. And I think this would be very important to, I don't know, get a bit of a theoretical sorting or understanding of all these algorithms that have been developed. Currently, what we can just do is measure in practice how well do they perform, and then we can make some statement, is this a good algorithm or a bad algorithm? And one last open problem I would find very interesting is that all these algorithms we mentioned so far, they just aggregate a lot of client models by just averaging the parameters. But we basically know the objective functions are non-convex, so averaging is not supposed to work well. So is there something better that we can do there to aggregate all this information that we get from the clients? Okay, thanks for listening, and I'm happy to discuss more in the breakout sessions.